Good morning. Today we will explore the fascinating world of computer architecture by comparing two foundational designs, von Neumann and Harvard architecture. My name is Mekwan Shoaib. My ID number is 22CS035. So these are the content that we will cover in this presentation. First, von Neumann architecture. A von Neumann architecture machine designed by physicist and mathematician John von Neumann is a theoretical design for a stored program computer that serves as the basis for almost all modern computers. It is characterized by memory unit, control unit, ALU, arithmetic logical unit, central processing unit, CPU. Von Neumann architecture, it uses a single memory for both data and instruction. So von Neumann architecture have the memory unit, control unit, ALU, and CPU to process the all instruction and data and processor instruction. Now hierarchy architecture. The hierarchy architecture is a term for computer system that contains two separable areas for commands and data. So unlike the previous one, the von Neumann architecture, the von Neumann architecture it have only one memory unit to store the data and instruction, and the hierarchy architecture it have two memory, that is one separate instruction memory and the data memory. So instruction memory contains all the instruction and data memory contains all the data, and other things are same as the von Neumann architecture. In this, the CPU fetched the next instruction and loaded data simultaneously and independently. It enhanced the performance. So key difference, memory organization. What is the difference between memory organization in von Neumann architecture and hierarchy architecture? So first, von Neumann architecture. So in von Neumann architecture, there is a single memory unit. This memory is used to store both program instruction and data, with the CPU accessing memory location sequentially as it executes instruction. It cannot simultaneously access data. So the latest computers, what we have like desktops, laptops that have the von Neumann architecture and hardware architecture, it employs separate memory units for data and instruction, and this separation enables parallel access. So meaning that the CPU can fetch instruction from one memory while accessing the data from another. The example that is a microcontroller like the AVR series. So we can see in this picture that the von Neumann CPU have only one memory for data and instruction. Both will be managed in the one memory space. And in hardware architecture, in hardware CPU, there are two memory, one for data and one for instruction. Now, what is the difference between instruction fetch in von Neumann and hardware architecture? In von Neumann architecture, there is a first fetch phase. The CPU sends a request to memory unit to retrieve the next instruction. The memory unit reads the data from the memory address and sends it back to the CPU. Second is decode phase. The CPU deciphers the fetch binary instruction. It identifies the operation to be performed and determines the operands for that operation. Third is execute. What is fetch and what is decode, then we will execute. The CPU carries out the actual operation specified by the instruction. And the fourth is write. If the instruction's execution produce a result that needs to be stored in the memory, or if it modifies a memory location, the CPU writes this data back to the appropriate memory address. The CPU fetch, decode, and execute instruction one at a time, following the order of instructions stored in the memory. So first, it fetches, then decodes, and then executes. So we see in this flow that fetch, then decode, decode, then execute, execute, then again fetch. This process is calling in loop. In hardware architecture, it handles instruction fetch by using two separable buses, as we will discuss earlier, that one for instruction and one for data. This allows the CPU to fetch instruction and data at the same time, which can significantly improve performance. So first is fetch, same as the von Neumann. The CPU sends a request to the instruction memory with the memory address of the next instruction to be executed, and the instruction memory reads and returns the instruction directly to the CPU. Second is decode and execute. The CPU decodes the fetch instruction, determining the operation to be performed and any associated operands, and execute the decoded instruction, carrying out the specified operation on the data stored in the data memory. And data access. During the execution, when the CPU needs to access the data, it sends request to the data memory. Data is read from or returned to the data memory as needed for the execution of instruction. So in a so we will see so there is a one flow that we can see in this flow, that CPU it fetches from instruction RAM and read from data and do as the instruction and write back to the data array. Example of von Neumann architecture. Von Neumann architecture is prevalent in various computing devices, particularly those designed for general purpose computing. One prominent example of a system that follows a von Neumann architecture is a modern computer. That's what we have, whether it is a desktop or laptop. These computers are designed for a wide range of tasks, from web browsing and word processing to a graphic design and gaming. So we can perform all these tasks because of the von Neumann architecture. So if it is a hardware architecture, then it is more complicated. In a PC, a single RAM stores both program instruction and data, facilitating sequential CPU processing. This versatility enables diverse application support. In a personal computers, we do not have to do all the heavy tasks. Heavy tasks means all the data, what we can call that, uh, all the data transfer. So heavy data transfer. So in a personal computers, we are doing only seamless. So we are doing any low level tasks like data entry and all of that. So it allows seamless multitasking, enabling diverse tasks like web browsing, document editing, gaming, and complex calculation on a single device. A prime example of hardware architecture. So this is for hardware architecture's example. So a prime example of hardware architecture usage is in modern microcontroller, commonly employed in embedded system for tasks like sensor data processing, motor control, and Internet of Things. The microcontroller employing hardware architecture, there are separate and dedicated memory space for program instruction and data. So this clear separation ensures that instructions are fetched independently from data, enhancing the efficient and real-time responsiveness. So these hardware architecture have two separate buses for instruction and data as we discussed earlier. So it enhances the efficiency and real-time responsiveness. Hardware architecture microcontroller ensures reliability and precision for real-time control tasks in robotics and medical devices and smart appliances. What is the advantage and disadvantage of von Neumann architecture? Von Neumann architecture is famous for its simplicity, flexibility. So it is a straightforward design, makes it easy to understand and program. Flexibility can handle a wide range of tasks and software application. It allows also a standard programming languages and development tools. What is the disadvantage? So it have the limited parallelism and it shared memory access. If we shared memory access, then it result in data transfer delays. Data transfer delays. Hardware architecture. What is the advantage in this? So advantage: separate memory for instruction and data enables parallel processing, leading to improved performance. And data security. Isolating instruction from data enhance security in some applications. Disadvantage: managing separate memory units can be more intricate and may require customized compiler to fully exploit the architecture. So we have to manage these two separate memory units. So it is a disadvantage of the hardware architecture, unlike all the advantages. So what is the application? So von Neumann architecture is suited for general purpose computation, that what we are doing, including the most personal computers. Like if we're doing coding and gaming and document editing and all of this stuff, then it should have von Neumann architecture other than hardware architecture. And hardware architecture ideal for applications requiring high speed data access. If we want in that industry, if we are going to go in that industry, then we need hardware architecture. The industry that require high speed data access, embedded system, and signal processing. Conclusion. So as we conclude, remember that architectural choices impact computing capabilities. Each architecture has its strength, and choosing the right one depends on specific application requirements. In the evolving tech landscape, hybrid approaches are also emerging to optimize performance. So as technology evolves, the architecture choices shape our computing capabilities. Understanding this principle is crucial for meeting digital world needs, be it von Neumann, Harvard, or future other architectures. Thank you.